Okay, can you see my screen?
Yep, looks good.
Okay, thanks, Charles. Hello, everyone. My name is Jianwei. I'm glad to introduce our project for you. It is application-aware G-SRv6 networking. Our plan is to develop G-SRv6 on the Linux kernel and combine G-SRv6 with APN6. Here are some related IETF drafts for your reference, and we have built up some open communities for you. Now let's talk about G-SRv6 first. As we know, SRv6 is the latest routing technology nowadays. G-SRv6 can resolve a critical problem of SRv6. The transmission overhead of SRv6 is too high. For example, if you want to use a strict TE tunnel with 10 seeds, the seeds will occupy 160 bytes in your packets. That is not accepted in interactive control and IoT scenarios, which packet length is under 128 bytes. So how about G-SRv6? The key point is G-SRv6 can reduce 75% transmission overhead. That means the size of seed list is cut down. Moreover, G-SRv6 can reuse the locators of G-SRv6. That means if you want to deploy G-SRv6, you don't need to apply for new IPv6 address blocks and advertise new IPv6 routes into your network. So you can deploy G-SRv6 incrementally and on your demand. It is full compatible with SRv6. By the way, there are about 12 vendors. Their devices have passed interoperability test of G-SRv6. Next, let's have a look at APN6. APN6 allows devices to identify application-related information and use IPv6 extension headers to convey the information along the packet to traverse the network. The information contains APP-ID, SLA level, bandwidth, delay requirements, and so on. So network can quickly adapt to specific SLA requirements of different applications. Okay, based on G-SRv6 and APN6, we present application-aware G-SRv6 networking. It combines their advantages to enable application-aware, fine-grained strict TE with lower transmission overhead. In this hackathon, we implement a demo for it based on Linux kernel and Huawei router. In detail, for G-SRv6, we build a kernel module to identify APN6 information and select the most suitable G-SRv6 TE tunnel for specific application flows. After that, it can encapsulate G-SRv6 routing header to packets. For APN6, we develop some functions to encapsulate APN6 options with application-specific information in IPv6 hop-by-hop options header. We set up a 3-layer topology for this demo, and we tested the performance between SRv6 and G-SRv6. In this demo, we programmed 3 TE paths for 3 kinds of applications. All of the paths are with above 10 hops. That means there are above 10 seeds in the seed list. The 3 applications are: first, file downloading with security checking in a service function chain. Second, interactive control, which is using leaf and short messages. Third, high-definition video on demand. For the result of performance test, we can see, first, forwarding rate of G-SRv6 is 55% higher than SRv6. Second, for the interactive control scenario, which packets contain only about 128 bytes in the payload, the transmission overhead is reduced by 50%. Third, we can see the bandwidth utilization of G-SRv6 is 10% higher than SRv6. Finally, for this hackathon activity, we can bring some feedback to working group. The most important is G-SRv6 can improve the utilization and value of bandwidth significantly and guarantee SLA better for applications. By the way, we have made some future plans. We plan to make some POC tests in wider area networks, such as CINI in China. And you are welcome to join us to improve this demo together. Okay, here are my teammates. If you have interest for our project, please send us an email. Thanks for your listening, and thanks to my teammates. Thank you.
Okay, well, great presentation. Yeah, thanks for getting us off to a good start. Does anyone have any questions before we move on to the next presentation?